Right, ladies and gentlemen, let's continue with chapter 9 on natural convection. We started with it yesterday, but unfortunately there was a technical problem with the data projectors. So I'm just going to show you some of the slides that I wanted to show you yesterday. As you can see here, we've got the egg, which is being cooled in air, and here the soda can, the buoyancy that I've showed to you. There is the derivation of beta in terms of writing it from densities, changes in densities to changes in temperature. That is the results typically of an interferometer. It shows as isotherms of constant density, and looking at that pictures we can get an indication of the streamlines. So here on the left would typically be laminar flow, and here on the right would typically be turbulent flow. That is the boundary layer that I showed to you yesterday with the velocity boundary layer, which is now different. Here we've got the velocity equal to 0, where previously it was equal to the free stream velocity. So that is what is different. This is the mathematics in terms of looking at a control volume, looking at the sum of the forces, going through the mathematics, and then using the boundary conditions, and then we end up with this term that I've showed you yesterday. So there we can see the Grashof number, and there's the Reynolds number square. So that is the definition of the Grashof number, and we use this ratio of the Grashof number to the Reynolds number square to get an indication of if the problem is a forced convection problem, a natural convection, or a mixed convection problem. In terms of the three examples I've showed you, this is typically where the Grashof divided by Reynolds square is much larger than 1. This is where it is smaller than 1, and that is where it's approximately equal to 1. So here we've got mixed convection or combined convection. Again, there is the equation of the Nusselt number that is written as a function of Grashof number and Prandtl number, and that product, because it occurs so many times, is called the Rayleigh number. That is the Rayleigh number, and we can always write it as a constant multiplied by a Rayleigh to the n, where the constant is typically smaller than 1, and the n value is approximately equal to a quarter or a third, depending on if the flow is laminar or turbulent. Table 9.1, I've mentioned that table. Here are examples of different types of surfaces with natural convection. We've got the flat vertical plate, an inclined plate, horizontal plates, then vertical cylinder, horizontal cylinder, and the sphere. For all of them, we've got the characteristic length is identified. You can see LL, and then suddenly it is the cross-sectional area divided by the perimeter. And there it is the diameter. So we have to be careful for that. And for all of that, depending on the ranges of the Rayleigh number, there are different equations that can be used. So let's do two examples. And the first example that I would like to do is that of a horizontal pipe with a length of 10 meters, the outside diameter of 100 millimeters, and the surface temperature of this pipe is 90 degrees Celsius. So it is an isothermal surface, which means that the temperature is constant all over the surface, and the environment temperature is 0 degrees Celsius. The question is to determine the heat losses from this pipe or cylinder. Right, going back to table 9.1, if you can just go back to that for us quickly, Tamarin, you can see there is the case of a horizontal cylinder. Okay, so that is typically what we have here. And for the horizontal cylinder, it says that the characteristic length that should be used is the diameter of the cylinder, so that's 100 millimeters, and then the range of that Nusselt number equation given there is valid if the Rayleigh numbers are smaller than 10 to the 12. So To get to the heat transfer coefficient, we obviously need to solve the Nusselt number. To get the Nusselt number, we need to get the Rayleigh number of the Grashof number. Okay, so let's start doing that. Firstly, we need to get the properties of the air on the outside, and we get it at the film temperature, which is equal to 90 degrees plus 0 divided by 2. So we would like to get the properties at a temperature of 45 degrees Celsius. Where do we get that? It is for air. You can get it in your textbook of Cengel and Ghajar in table A15. All the values are given. And these values are, firstly, a thermal conductivity K of 0.02699 watts per meter Kelvin. Prandtl number of 0.7233, kinematic viscosity of 1.772 multiplied by 10 to the minus 5 square meters per second. And then the last one we need to get is beta. And if you look in that table, you'll see that the values of beta are not given. As discussed yesterday, if the fluid which is being considered can be considered as an ideal gas, then we can just say it is equal to 1 divided by the film temperature. However, take note, this should be in Kelvin. Okay, so it is 1 divided by 273, and our film temperature is 45. So it is 1 divided by 273 plus 45. That would be the value of beta for air. We can see in the equation that we need the Grashof number, or actually the Rayleigh number. Okay. Now, the Grashof number by definition is equal to G beta multiplied by the temperature difference multiplied by L to the third divided by the kinematic viscosity square. And this L is the characteristic length. Okay. How do we get it? We need to look at the fine print, and if we look at that table, we can see that the characteristic length is defined as the diameter in this case. So let's calculate the Grashof number based on the diameter. That is why I'm using the subscript. It's equal to G, which is 9.81, multiplied by beta, which is 1 divided by 273 plus 45, multiplied by the temperature difference, which is 90 minus 0, multiplied by the diameter, which is equal to 0.1 to the third, divided by the kinematic viscosity, 1.772 multiplied by 10 to the minus 5, and it's the square of it, and the result is that we can calculate the Grashof number based on the diameter as equal to 8.838 multiplied by 10 to the 6. Okay, do you all follow that? The equation wants the Rayleigh number. So the Rayleigh number is equal to the Grashof number multiplied by the Prandtl number. It's of course now also the Rayleigh number based on the diameter. It's equal to the Grashof number that we've obtained just now, 8.838 multiplied by 10 to the 6 multiplied by the Prandtl number, and the Prandtl number is equal to 0.7233. And the result is a Rayleigh number of 6.393 multiplied by 10 to the 6. Cameron, if you can just go back to the PowerPoint for us, please. So if you look at the horizontal cylinder here, you'll see that the Rayleigh numbers should be smaller than 10 to the 12. We are smaller than 10 to the 12, so we are fine. And therefore, so that's in range. And therefore, we can then calculate the Nusselt number as 0.6 plus 0.387 multiplied by Rayleigh number to the 6 divided by 1 plus 0.559 divided by the Prandtl number to the 9/16, and then everything to the 8.27 and everything squared like that. And that is equation 925 in your textbook or in the table. Equation 925. Okay, so a little bit, some work to go through it, to calculate it, but you'll see that there are just two unknowns. The one is the Rayleigh number, and here we've got the Rayleigh number, which is of course the Rayleigh number based on the diameter, and there's the Prandtl number. The Prandtl number we get from the properties is equal to 0.7233, and the result is if we go and calculate the Nusselt number, then it is equal to 24.83. Is that clear to everybody? Right, if we've got the Nusselt number, then it's very easy to get the heat transfer coefficient, because the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. The Nusselt number is equal to 24.83, is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity is equal to 0.02699. And from this, we can solve the heat transfer coefficient as 6.701 watts per square meter degrees Celsius. Now in chapter 1 of your textbook, or chapter 2, I don't know if you can remember, when the three different modes of heat transfer were discussed, a table was given of typical values of heat transfer coefficients. And an answer like this is actually very important in terms of the range, what you can expect. So normally, if we've got problems of natural convection, then the heat transfer coefficients are the order of magnitude up to maybe 10 or 20 or 30 like that, but relatively small. If we've got single phase, water, air or something like that, with forced convection, then normally the heat transfer coefficients are order of magnitudes of thousands. If we've got condensation or boiling, then the heat transfer coefficients, order of magnitudes, are about tens of thousands. So this is always something that is very important for you to realize that most probably the answer is about right. If the answer was 6,701, then you sort of should know it can't be, I've made a mistake somewhere, let me just go and check. Right. So now that we've got the heat transfer coefficient, let's calculate the heat transfer rate. The heat transfer rate is then equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T infinite. The heat transfer coefficient is equal to 6.701. The surface area through which the heat transfer is going to occur is going to be the outside surface area of the pipe, and that is equal to pi multiplied by the diameter multiplied by the length of the tube, multiplied by the surface temperature, which is 90, and the environment temperature, which is equal to 0. So therefore, the heat transfer rate would be 1,895 watts. So the heat transfer rate in terms of the losses are approximately 1.9 kilowatts of heat. Are you all happy with that answer? Well, I was hoping there was somebody that would tell me, no, he's not happy. Because there's something that we've missed. And what we've missed is, and again it's in the fine print of this chapter, is that normally with natural convection problems, radiation plays a big role. So this surface is at 90 degrees and the environment is at 0 degrees. Now you've already done the 2 chapters on radiation heat transfer. And we actually have to take radiation heat transfer also into consideration here. So let's call that QC, which is the convection losses, and we go and calculate the radiation losses. And the radiation losses can be simplified by the emissivity multiplied by sigma, AS multiplied by the surface temperature to the 4th minus that of the environment to the 4th. Now they didn't give us the emissivity, or they didn't say anything about the walls on the outside, at what temperature that is, but let's assume that this pipe is somewhere in a building and the temperatures of the walls are approximately equal to 0. And we sort of would like to know what would the maximum heat transfer be, the maximum radiation. And that would be for a emissivity of equal to 1. So this is just an extreme worst case estimate of what the radiation heat transfer can be. So it is equal to 1 multiplied by the Stefan Boltzmann constant, 5.67 multiplied by 10 to the minus 8, multiplied by the surface area, which is pi, multiplied by the diameter, multiplied by the length of the tube, multiplied by the surface temperature, which is 273 plus 90 to the 4th. Take note, not in degrees Celsius, but in Kelvin, minus 273 to the 4th, because it's at 0 degrees Celsius. And there's the equation. And if we go and calculate the radiation heat transfer, it would be 2,103 watts. Thus, if we look at this, we can see that the natural convection losses is 1.9 kilowatts, and the radiation can be up to 2.1 kilowatts. Now, yes, it might be that the emissivity is 0.5, then that would be equal to about 1,000 watts, so 1 kilowatts, but you can see that it has a significant contribution to the total. So in this case, the total heat transfer rate would be the 2 together, and if we calculate that, it is equal to 3,998 watt, which is 4 kilowatts of heat losses from that tube or pipe. Any questions? Nothing? Okay. Let's do in a second example. And in this example, we're going to use... Yep, sorry, there's a question.
Use the log mean temperature for your heat transfer.
Why didn't we use the log mean temperature? Well, in this case, if you can just imagine the outside of the surface, the surface it has been given is 100 degrees Celsius, is constant. Okay, so if you go and plot it, then that would be 100. The beginning of the pipe, and at the end of the pipe it will still be 100. The other source of temperature is that of the air, and that is in a room. So there it will also be 0, and there it will also be 0. So do not confuse natural convection with using the LMTD from the convection cases. In the convection cases, where we had a surface, we had a fluid flowing along that surface. Okay. And as you can remember, there are 2 cases, the case of the constant heat flux and the case where we've got a constant wall temperature. So there was heat transfer from this stream to a fixed wall, but the temperature would change all the way. So it's a little bit different in terms of configuration. When we get to the last chapter on heat exchangers, there we're going to have always two streams. So you're going to have a heat exchanger through which the flow is going to flow through there, and then maybe on the outside you're going to have the flow through there. And in these cases, where you've got two streams, we will always use the LMTD approach. Okay? Did I answer you? Okay. Right. The next problem is going to be a flat plate. Like, let's suppose this textbook. And let's suppose this surface is being heated to a constant temperature. And this surface is insulated. Okay. Now, if I keep this surface like this, there will be obviously natural convection to the air. Now, if I would look at the heat transfer like that, and I would turn the plate like that, or like that, which one will give us the most heat transfer to the air? Who of you would say if you keep it like this? This is the hot part. Right, like that, and like that. Okay, so let's see. So this example is based on example 9.2 in your textbook, but it is different. So in this example, we look at this plate, which is 0.7 meters in that direction and 0.9 in that direction. And on this side, it is insulated. Okay. And this is the part which is being heated. And the surface, TS, is at 100 degrees Celsius. And the environment temperature is 20 degrees Celsius. Okay. So this is the case where we've got a vertical plate. If we can just look at the PowerPoint again, Tamara. There we go. There's the vertical plate, and here we can see one side is insulated, and on that side it is being heated. It tells us that the characteristic length would be in that direction. That is the range of the Rayleigh number. There are three equations that we can use, and in all those equations we need to get the Rayleigh number. To get the Rayleigh number, we need to get the Grashof number. Okay. So that is where we're going to go with this. Let's look first at the properties. So the properties we have to get at the film temperature of 100 plus 20 divided by 2, that is at 60 degrees Celsius. So again for air, in table A15, there we get all the properties of air, and in this case it would be a K value of 0.2808 watts per meter Kelvin. Prandtl number is equal to 0.7199. The kinematic viscosity is equal to 1.92 multiplied by 10 to the minus 5. And we need the value of beta. And beta again, because we can say air is an ideal gas, and the values of beta are not given in the table. So we can say it is equal to 273 plus 60 degrees. The Grashof number. In forced convection problems, the first thing we almost always did was getting the Reynolds number, because the Reynolds number told us it's flow laminar or turbulent. In natural convection problems, we always need to get the Grashof number. So the Grashof number is equal to G multiplied by beta, Ts minus T infinite, multiplied by the characteristic length to the third, divided by the kinematic viscosity, like that, square. Okay, G is equal to 9.81. Beta is 1 divided by 273 plus 60. Surface temperature is 100 minus 20. And now the characteristic length. The characteristic length, that is our direction of G. If we go back to the PowerPoint and look at table 9.1, which one of the two dimensions should we use? Should we use 0.7 or 0.9? It shows that it is the length in this direction. You see? So it is 0.9 meters. I hope you still remember that with the previous lecture I've told you that if you look at the statistics in terms of in the exam, where most students make their mistakes, it is to get the characteristic length. They are not careful enough with that. And the other one is getting beta. If it's an ideal gas, you can use this equation, but if it's not an ideal gas, if it is water or anything else, or steam, then you need to get it from the tables. So it's very simple. If it's not in the table, most probably it's an ideal gas, and you can use the ideal gas equation. The kinematic viscosity is equal to 1.92 multiplied by 10 to the minus 5 square, and the result is a Grashof number of 2.192 multiplied by 10 to the 9th. The Rayleigh number is the Grashof number multiplied by the Prandtl number. The Grashof number we've determined just now, 2.192 multiplied by 10 to the 10th multiplied by the Prandtl number, and the Prandtl number is equal to 0.7233, and the result is a Rayleigh number of 1.578 multiplied by 10 to the 9th. Right, let's look at the equations. We can see that for the vertical plate, the first range is 10 to the 4th up to 10 to the 10th. The next range is, remember there's an error, 10 to the 10 to 10 to the 15 or 19. So it seems as we're in that range. And then there are two different equations that we can use. And then there's equation 921, which is valid for the total range, the extreme, the entire range. So in this case, I just want to bring it to your attention, table 9.1. I've told you yesterday there's an error in it with a range, but also take note that while I remember that there are also errors in those two equations. Those values are incorrect. For those of you who don't have it in your textbook, it is in your study guide, all the corrections that you need to implement. So please make sure you do it, because if in the exam you're going to use the wrong equation, it's your own fault, unfortunately. Okay, so please take note of that. There are 3 errors in this table. Right, now, although I can use one of the simple equations, I've solved it using equation 921. And I'm just getting tired if I must think of writing it out, equation 921, and putting in all the values. So I hope you'll forgive me. I'm going to skip that, and I'm going to give you the answer as Nusselt number is equal to 141.8. Okay. So equation 921, you see the equation there, you just need to put in all the values of the Prandtl number and the Rayleigh number. Okay. And that is the result, 141.8. From this, the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by K. I've said the diameter, but it should actually be the characteristic length, LC. The Nusselt number is 141.8, is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity, 0.2808, and the result is a heat transfer coefficient of 5.678 watts per square meter degree Celsius. If we look at the answer, it looks right. It is not hundreds or thousands. It's a typical value for natural convection, order of magnitude approximately 10. Right, so again, calculating the heat transfer from the natural convection only would be equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T infinite. The heat transfer coefficient is equal to 5.687. The surface area is 0.7 multiplied by 0.9. So take note, the plate is not heated on both sides, it's only one side. On the other side it's insulated. And then the temperature is 100 minus 20. And the result is a heat transfer rate of 286.6 watts. As I've mentioned with the previous problem, radiation normally plays a big role in natural convection problems. Here we've seen it. You've seen how we can calculate it just using an emissivity of 1, surface area, the equation, etc. So if you go and do that, you'll see that the radiation heat transfer is going to be approximately 428.2. So it's almost double than that of the natural convection. However, take note, this was calculated now with emissivity of 1, which is not an accurate value, but maybe 0.5, and then it would mean in any case you're talking of more than 200 watts. So it will almost double that. So the total heat transfer rate would be 714.8 watts for the plate in a vertical configuration. Any questions? Right, now let's do it now for the case where the plate is like this. Okay, there it's insulated. That is 0.9 and that is 0.7. So the hot surface is now this surface here. The top. We go to the textbook at the table 9.1. We can see that here we've got a horizontal plate with a hot surface there. However, take note of how we should calculate the characteristic length. Okay, it is the surface area divided by the perimeter should be used. And there are the equations to be used. So the characteristic length is equal to the surface area divided by the perimeter. The surface area is 0.9 multiplied by 0.7 divided by the perimeter is of course 0.9 plus 0.7, and it's 2 times that. And the result is a characteristic length of much smaller than any of the 2 dimensions. Characteristic length of 0.1969 meters, about 200 millimeters characteristic length. We need to use this now to calculate the Grashof number based on the characteristic length. That is equal to G beta Ts minus T infinite multiplied by the characteristic length to the third divided by the viscosity square. G is equal to 9.81. Beta is 1 divided by 273 plus 60. The surface temperature is What was it again? 100 minus 20. And the characteristic length that we've now calculated is equal to 0.1969. Divided by the kinematic viscosity square, you can just substitute the value there, and the result is a Grashof number of 4.877 multiplied by 10 to the 7. Once we've got the Grashof number, we can calculate the Rayleigh number. The Rayleigh number is equal to the Grashof number multiplied by the Prandtl number, and that works out as 3.511 multiplied by 10 to the 7. So you just take this Grashof number multiplied by the Prandtl number, and the Prandtl number is equal to 0.7199. Therefore, if we look at that, then the Nusselt number should be equal to 0.15 Rayleigh to the third. That is equation 923. You agree? You'll see that in the table, there's a range of 2 to the 4 to 2 to the 7. Okay. For the first range, and the second range is 10 to the 7 to 10 to the 11th, so we have to use the second one. And for that, the Nusselt number is equal to 0.15 Rayleigh to the third. In your textbook, it says only 0.1. It's a misprint, remember? It should be 0.15. Okay. So, we've got the Rayleigh number, there it is. We just need to substitute it in there, and from that we can get the Nusselt number, which is equal to 48.83. The Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. The Nusselt number is 48.83. Is equal to the heat transfer coefficient multiplied by the characteristic length, which is equal to 0.1969, divided by the thermal conductivity, which is equal to 0.2808, and that gives us a heat transfer coefficient of 6.977 watts per square meter degree Celsius. If we compare this heat transfer coefficient to that of the case where we had the plate in a vertical position, we see that the heat transfer coefficient is higher, which means that the convection heat transfer is going to be more. So from that you can go and calculate the convection heat transfer. I'm not going to write it out, but it is equal to 351.1 watts. The radiation is equal to 428.2 watts. And that gives us a total heat transfer rate of 779.3 watts. 779.3, which is higher than that value of keeping it in a vertical position. Okay? You all follow? Right, the last example, which I'm also just going to solve very cryptically with you, is now again this plate like that. Okay. And there's the bottom surface. And now this bottom surface is the one which is being heated. Like that. So the temperature here at the bottom is equal to 100 degrees Celsius. Okay. Take a look at the equation that should be used for this case. Here we've got the hot surface here on that side, and there is the range and the Nusselt number equation. However, the characteristic length should also be determined by the surface area divided by the perimeter. Okay, so again, the characteristic length is equal to the surface area divided by the perimeter, and that stays the same. Okay. So it is still equal to 0.1969 meters, and because that is the same, the Grashof number and the Rayleigh numbers are going to be the same. So the Grashof number, which is equal to 4.877 multiplied by 10 to the 7, the Rayleigh number is equal to 3.511 multiplied by 10 to the 7. And the equation to be used, the Nusselt number is equal to 0.27 multiplied by Rayleigh based on the length to a quarter. Different equation. The Nusselt number is going to be 20.71. The heat transfer coefficient we can get from the Nusselt number. The Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity is equal to 20.78. So it gives us the heat transfer coefficient is only 2.945 watts per square meter degree Celsius. So it's the lowest of the three. And with that, you can go and calculate the convection losses. It's going to be 149.4 watts. The radiation is going to stay the same. It's going to be equal to 428.2 watts. And that would give us a total heat transfer rate of 577.6 watts. So, of the three cases, this one will have the lowest natural convection. It will take longer to cool than any of the other two cases. Yes, then you need to go to literature and you have to go and get an equation, or you have to do your own experiments. That happens a lot, that you end up with values that are not in range. Now again, discretion is always an important thing to an engineer. So if you look at this case of a Rayleigh number was a 10 to the 5. Oopsie. Yeah. If I would have a value of 5 multiplied by 10 to the 3, it would be close, isn't it? So then I will take the chance and I will use it. But again, it will always depend on how critical your design is. Do you do the calculations just to get an order of magnitude idea of the problem? Or are you competing against other people for a tender or for a design? And if you do that, then obviously you need more accurate information. Yeah, it happens a lot that the ranges are not in that of the textbook. Remember, the textbook is just a selection of some of the most important literature. If there's no textbook that actually contains everything, I think it would be something like that, just on natural convection, you know, all the data that's available, all the graphs, everything. Okay. Right, ladies and gentlemen, then I'm going to use the last minute. I don't normally like to use PowerPoints to give class with, but with the previous lecture, I've showed to you the cases of fin surfaces. The fin surface, what is now important is that we've got this distance x, s, between the fins. We've got the distance x between the fins, and we've got the length L. And it's all about optimization. So this has been done for typically electronic cooling products like that. There you can see all the different types of fins. And depending if it is a constant surface temperature problem, take note, Ts is equal to constant, then the Nusselt number is typically being given by that equation, and it can be optimized. You can go and calculate what should be the optimum distance between it, and there you can see the equation for it, and you will also see that the Nusselt number would then be equal to 1.3. What does 1.3 mean? It means that the heat transfer would be 30% more than that of conduction heat transfer only. So you score 30%. Then you can also have the case where it's not a constant surface temperature, but a constant heat flux. Again, the same type of problem, and then you've got another type of optimum. Excuse me. The S optimum is the spacing in between has been optimized. You can use that equation for it. And then the last part is where we've got enclosures. A classical example is a window. Many of the windows not really in South Africa, but in other countries where the climates are much colder, there a double glass is being used. This is being sealed, and this is being vacuumed in terms of trying to minimize the losses. Now, if this is cold and that is hot, you're going to get natural convection here on the inside. Okay. And again, depending on if the enclosure is like that or if it's tilted, you'll get different types of heat transfer in it. And again, the information is here in the textbook on how to get the heat transfer coefficients depending on the characteristic length in terms of different types of configurations. Again, the fine print is the important thing, and getting the characteristic length. So reading very well to get the characteristic length. You've got the characteristic length, you're going to put it in the Grashof number. The rest of the Grashof number things are all the same. It's the G, it is the delta T, etc. The only thing, the beta, that you have to be careful for, and as I've mentioned, in many cases, if it's a gas, in most cases you can assume that you can use 1 divided by the temperature in Kelvin. Other cases, if it's not a gas, then use the values that you can get in your textbook. So there's everything. And specifically for those of you who are interested in the heating and ventilation and air conditioning industry, glass is a very important thing. And there's at the last part of the chapter, there's quite a lot of material there, which is still just introductory type of material. So please just take note of that. And then with the next lecture, I'm going to do a problem where we're going to have mixed convection. So that is the combination of natural convection and forced convection. Ladies and gentlemen, thank you very much.